The concept of lightning and sharing model is basically, yeah, the property of light actually, right? Lighting and shading, um, with it depends on what type of lighting we have and what does the lightning property has. And when it comes to the shading part, which are there are many considerations which we need to go through when there is some shading happening, because the source of light, at what angle it is incidenting on the object, right? And uh, it also speaks about, is my particular ray of light falling on the normal of a plane, or it is falling on the just on the other side? Where should the shiny part be there? Okay, if it is the shiny part, what about the object? Is the object shining, having a shining surface, or it has a rough surface, or it has a irregular surface? Do we have any reflection of light on the object? Many of these considerations have to be taken, right? So, of course, lighting and shading has been taken from your model, from your Edward Angel textbook, chapter 6 and 6.1 to 6.4. So, properties of light. Okay, yeah, within this, we also learn about the lightning models, reflection models, normals, and color. So for now, you people know about, there we had light sources, and we have only 2 point sources which we saw in the particular slide from your other textbook, right? But we actually have uh, 4 to 5 types of light sources. One is the ambient light, so no identifiable source of direction. That means we don't have a source from where we actually get the light source, right? That means we are just getting the shower of light. For example, you have a cloudy weather in Bangalore. Can you identify where exactly the sun is? Do you know where exactly the sun is? Because it's very cloudy and we cannot even track where the light is. Best example for the ambient light. Best example for the ambient light is the cloud. I mean the where which is stopping the sun rays entering into the Earth's surface directly, right? So it is giving us, what do you call, a matte sort of light, right? So ambient light has that property. Ambient light has that property. The second one is point source. Best example is, we have a reading or a bulb, right? We can take it as a bulb. Bulb is a point source, right? Given only by point. Means at a single point, the light has been generated and it is moving towards the other sides. So that will be the ambient light. We also have, I mean, sorry, that will be the point source. And we have the distant light. Okay, when we get a rays of sun, but we don't have any clouds between. If we have clouds, it becomes ambient light. When we do not have any cloud, then it becomes a distant light source. Correct? So last class we have spoken enough about the distance light source, and because in the light source, distance light source, the distance will be very like infinite nearly, where the rays of light normally becomes parallel to each other. So spotlight is given only for that particular area only. We saw the spotlight in the last class with the cone like a structure which we saw that comes under the spotlight. So from source in direction, cutoff angle defines a cone of light. So in this cone of light, we have some issues. So what is that issue? We call it as an attenuation. The attenuation refers to some part of the given area will be very bright, and again the rest will be less brighter. And again, uh, in other words, as we go away from the center of those spotlight, you can experience diminishing of light, or the brightness will come down. That's the best example for a spotlight. The light source described by a luminance. Luminance, as I said, separately, right? We saw, what was that? I'll show you. So here, as I said, we have a luminance in the sense we have many light sources. Each light sources will actually be individual to each other. So what we did, we created like a grid. So each box actually is a light source. Okay, so each box is emitting its own radiation, I mean own rays, right, in all the angles, in all the angle. Basically, it is coinciding with many of the light sources here which we have. So each color is described separately. Each color means each light source will be described separately. Then in the light sources, uh, we have the intensity. Intensity, again, it depends upon the color, right? If I have more red light, more red intensity of light. Similarly, more with green, more with blue, it depends on that. Okay, where I stands for intensity, intensity of red, intensity of green, and intensity of blue is what the luminance or the brightness or the whatever the light source which we have. Sometimes calculate generically applying the RGB colors, right? And is about the first thing we speak about the ambient light, which we have with the common types of light. So ambient light is having with the intensity is the same at all points. Is same at all points. Example for ambient light is the clouds are covered, right? So you people say whenever there is a dim light, you say the ambience is very good in this particular room. But still, ambience here refers to where the intensity is the same at all the points. There is not much difference between the ambient light and a distant light source, but in the ambient light, usually it will be very dim, nearly. And when it comes to the distant light source, it will be, the rays will be parallel. That means the intensity will there be same, but it's of a bit higher than the ambient light. So this light does not have a direction, as I said, or it is the same at all the directions. So my intensity IA will be equal to intensity of ambient earth red, intensity with ambient of green, intensity with ambient of blue. So this is the formula for the intensity of ambient light. Next is about the point source. So remember, these are actually the values which you can actually see here, right? This particular note here speaks many things which are actually not present for what is necessary for you, and that is why we're just going across the simpler stuff, simple way of understanding, and later we can easily decode it. So ambient light is IAR, IAG, IAB. And with respect to the point source, the intensity of the point source is given by IP naught. It is a point source, and we actually write it in a form where IP naught or intensity of a point source will be equal to intensity of red in that point, intensity of green in that point, intensity of blue in that point. So intensity decreases with the square of distances. What do you mean by square of distances? Yeah, let's speak about that. As I said, I have a point source here. Let's assume it's a bright point source. Okay, so what are the properties of this? Okay, what is the property of it? Can I take this in particular? Okay, so the intensity of the light, I'll take a very light color. So the light rays will be falling on all the sides, let's assume. So let's assume this is the sides which it is moving. Okay. So it moves on the other side too. So this is what a point source. A point is over here and it is illuminating light on all the directions. That's what I said in the last class. If I have any object, let's say black is okay, white will be the better one. So I have an object here. So this object will be much more brighter here. This object will be much more brighter here in the sense this is very closer to that of very closer towards the point source, right? That's why it is looking pretty bright. If it is going away from the light source, obviously the intensity gradually decreases. The intensity gradually decreases. Furthermore, it will be much more darker. It will be much more darker. Now, anybody would like to tell me why does this happen? Why does this happen? And so later it will be a black color anyhow. The background is black itself. Yeah, why does this happen? No, you people who have studied physics and much more in engineering too. So here, as the distance between the object and this point source, if it is going more, that's what the equation says. If it is more, the intensity, if the denominator is going more, if denominator is growing more, the numerator, the overall value will be less, right? If the denominator is less, the overall value will increase, right? So P minus P naught in the sense P is nothing but your object and P naught is the source of light, all right? So intensity from source to the object will be directly depending upon the square of its distance between the object and the light. So as you go away, the intensity of reaching this object will be very less. That's one way of understanding the point source. Next is one limitation of point sources. Yeah. So of course, when we speak about a small pin like structure, when we have a distant sun and we have a small object here, let's say a pin, the layers of light reaching that object doesn't make any sense because it is infinitely small. So the rays will overcome and we don't have any issues with it. But in case of an eclipse, what kind of eclipse? The lunar eclipse, or okay, we call it as a summer eclipse. Okay, so solar eclipse, I guess, where moon is in between the sun and the earth. So we have an eclipse. That means this moon is considerably, somewhat, can be relatable to the size of the sun, and over the distance, I cannot say that this distance is now infinite. This distance is now finite. Why? Because the object, it depends on the object which we are actually considering too. Right? As the objects, I say, grows bigger and bigger, the light rays which is moving from here, from this side to this side, and this side to the other side, they bend, right? And also the light source which is falling in this way creates a region which is called as a penumbra region. That means the shadow of this particular moon will be falling on this particular place. On where? On Earth. On where? On Earth. Right. So this will be your solar eclipse. So one limitation of a point source is you get variation with the intensity. Why? Because you have a dark black background which you have on center of the distance of, the center of the surface. On the other side, we don't have any issues. Okay, so over here we don't have any issues. Over here we don't have any issues. Distant light source, we have spoken much, given by the vector v. Intensity does not vary with distance. All distances are the same. That means infinite. Best example, sun ray towards the earth. Spotlight, most complex light source in OpenGL. Why? Because it's complex. Why? Because it is spot. It is, we have to provide it only for that particular space with some angle theta. Right? We also spoke about the attenuation problem which we have in this particular spotlight. So what do you mean by spot attenuation? Spot attenuation is nothing but you get on off on off on off sort of intensity. Why? Because my light source will be sent to one particular angle only, right? Whatever this light again, it will be moving in many directions. So sometimes it will be like bouncing on the surface, and somewhere it will come out, right? So the place where it may come out depends on the rays which it is following. That's why it forms alternate rings. Alternate rings. That means here it will be bright, here it will be very bright, here it will be not bright. All right. So then again over here it will be very bright, and on the other side it will not be bright. So alternatively, dark and light particular sort of image will be occurred. So spotlight is brightest along IS with respect to the intensity of S with center vector V and phi from P to point on surface, intensity determined by cosine of phi corresponding to projection of V onto IS. So spotlight exponent E determines the rate. So I equal to cos E phi, which is equals to V dot intensity of spotlight over E. So for E equal to 1, we have this value. For E greater than 1, we have some curve narrows. So intensity bends. For any of these, okay, we have a particular example for that. Now we can think about how is reflected on a surface. Yes, this is a wonderful, this is basically what we had, what I had thought for today. Now we can think about how the incoming light is reflected by a surface. So if you have a very bright surface, very bright in the sense very shiny surface, what happens when you pass light on that? What happens when you pass light on a very bright surface? For example, a steel vessel. What happens when you pass a light on a steel vessel?
Light reflects, sir.
Light reflects. Why light reflects on whenever the ray of light falling on the steel vessel? What are the property here? What made light reflect when it falls on the steel surface, and why will the light will not reflect when it falls on wood, on floor, on cloth, on book? That's what I can see from here. Yeah, why doesn't it reflect? Why doesn't it reflect, guys? Don't know. It reflects because it is having a shininess on the object. Okay, the less the shininess, the less the dim. I mean, more the dim. More the shininess, less the dim. In other words, it will be very sharp and reflective surface. So when do you call it as a reflective surface? When light hits on opaque surface, some is absorbed, the rest is reflected. This can be transmitted to, but we don't want the reflected light to be falling on something else. First, the reflected light is what we see. The reflected light is what we see. So if you look into this diagram here, we have a surface, incident light, which is falling on a particular surface at each particular point, and from there the light gets reflected. Why? Because it is a curved surface. It is a curved surface, and this particular ray of light will pass through the camera or your viewer, and what we can say is this particular light rays can be captured by a viewer or a camera. The reflected light is what we see. Reflection is not simple and varies with material. The surface, micro surface define the detail of reflection. What does mean by the surface? Microstructure define the detail of surface. Sorry, reflection. Here, my surface can be smooth or it can be having a rough surface. Okay, so what happens when the light falls on this particular thing here? It may not reflect in this way, it may reflect in this way, it may reflect in this way, it may reflect in this way. So not uniformly it will show on this particular direction, it may not show. All right, so it also depends on the microstructure define the detail of reflection. Variations produce anything from bright specular reflection to dull matte finish, that is your chalk-like finish. Okay, specular reflection means mirror finish. Okay, I guess we understood this. Do we have any doubts here, guys? Surface reflection. All right, if not, we'll move on to something called as Phong lightning model or Phong illumination model. Calculate the color for arbitrary point on surface. Basic inputs are material properties, that is I, N, and V. So what is I? The light source, L light source, N is normal to the surface, and V is with respect to the viewer. All right, so this is assuming that this is our surface. Not all the time the surface will be flat. The surface can be irregular. The surface can be bent. The surface can be shiny. The surface can be dull, right? So whenever we have the intensity or the light source which is falling on the particular surface, and it can have a reflection of the light I. Okay, so light surface, it is from here, it is falling on the particular point and it is reflecting. And we also have a normal. Normal is a perpendicular line which is drawn towards perpendicularly on the surface. P refers to the point in which the light is incident on, and V is nothing but a viewer which is capturing the particular light. Light which is forming on this particular surface will be very bright and shiny, depends on the surface, and gradually the intensity decreases on the other side. This is about the Phong illumination model, which you can basically see. And in that illumination model, we have some basic calculations. Calculate how much primary colors are falling. Start with global ambient light. Add the reflections from each light source. Because red has red reflection, green has a green reflection, and basically blue has its own blue reflection, right? So it falls between 0 and 1. Reflection composed into 3 forms: ambient, diffuse, and specular. Based on ambient, diffuse, and specular lighting and material properties are differs. Okay, so first we'll look into the ambient, then diffuse, and then specular. Okay, so we'll first understand what I mean by specular first, because I have one program which speaks on specular. Yeah, so there is something called as reflection coefficient. Reflection coefficient refers to, on this particular surface, the reflection is very high. If you zoom it, you can see the light source which is in a circular form. If you zoom it, you can see a light source which is in a circular form, and it is a very shiny surface, which is a very shiny surface. So specular reflection has a coefficient Ks. This Ks is lying between 0 to 1. 0 is very dim and 1 is very high, very bright. Shiny surface is very high specular coefficient. Shiny surface will be nearly 1. Used to model specular highlights, but do not get mirrored effect with the technique. So specular reflection will be evenly, it will be moving on. Okay. So shininess coefficient we spoke about. What do I mean by shininess coefficient? So shininess coefficient is the alpha value which we look into. Light S is specular component of light. That means light is falling on the surface. As the surface on this surface, the intensity is very high. As the surface goes on, so here in this particular surface, it is coming towards the less, very sharp, very sharp. Um, it is decreasing very sharp. So what about here? And over also, as we come towards on the other side, the shyness coefficient will just go off. Okay, it will not be there. So R is a vector of perfect reflection of L about N. V is a vector to viewer. Phi is angle between. Alpha is the shyness coefficient. Composite, I mean, how do we understand that shyness coefficient is intensity of specular will be equal to the coefficient of specular, and the light component Ls cosine of the alpha with whatever the angle which we are sending, the angle between viewer and the reflected surface. So that's about the specular here. Let's see with how exactly a specular can be seen in the case of example. So this is how the specular looks like. The specular contents look like in graphics. So what have we done? We'll just look into the example here, starting with main. You know about the single buffer, RGB and depth, because no movement, colors I have used, and it's a 3-dimensional view which we are giving. Size, window size is 500. So here, yeah, init will go to init. So in the init, what we have is we are giving the matte specular as with the intensity of values all 1. So here the shyness coefficient is 50. Light position is 111 and 0. So we are clearing off the color. Then the surface model is smooth. You can see a smooth surface here. And what is the material property which we have? We have front, we have specular, we have a matte like value. All these values, that is matte, specular, is this value. Okay, we need to send what will be the surface value. We will also change these values and we'll see how exactly it looks like. And matte shininess, what will also decrease this value and make it as a dull. And what about the light and light's position? Light position also has few values in it. We'll look into it. So GL enable, GL lightning, we are using the lightning facility, light 0, and we also have to get the depth test. So these are the enabling values, telling the program that I need these effects. Then we'll come to the init is done. Then we come to display. So display is pretty simple. We are using some GL color buffer bit and GL depth buffer bit, clearing those previous values. Then I'm creating a solid sphere. I'm creating a solid sphere. So if you increase this 0 to 1 is what the size. If you make it as a 2, it will be a very big. And it has some values of 20 and 60, where it speaks about how many sides do we have. All right. I mean, how is it an exact round, or is it okay if it has nearly cut sides? All right. So then basically we are just telling that at one particular angle we are giving the light sources to whom? To the solid sphere. All right. So this is the example, and reshape anyhow, if I move this object, it will be varying with the width and height. So that's what the width and height of a program is telling. Okay, that's about the reshape. We have seen much of the reshape examples previously. So see to this is having an intensity of 50. The coefficient, shininess coefficient is 50. All right, so let's make it as 150. Yeah, it takes a bit time. My machine is pretty old, and it has to draw, it has to render. It takes a bit time at each execution. Can you see the shininess coefficient now? So I have made it pretty bright, right? I have a very perfectly like shiny surface. So this intensity speaks about it. All right. So the smart shininess is what we have to give towards the material property of the object. Okay. So let me give it as just 10. Let me give it as 10 and we'll execute. So here it gives a bit dull, than that of 50. Okay, I'll just give one shininess, and it will be very dark. It's a very dull sort of. So yeah, that's about this value, and yeah, here when it comes to the shape model, it's not only GL Smooth. We also have something called as a Gouraud shaping. Okay, we have some other shaping also. Does it suggest? Okay, it does not suggest. Okay, so GL smooth, that means we have a smooth surface here. So we'll come back to this. Then we are actually giving the we are clearing the color with the background, right? If you want any of the values to be specified, we can change those values. And here, with respect to the materials, we have the front, and that means we have the face. We have the face of material, that is the front of it is what we want to see, and the second one is what type of surface it is. So it's a specular surface, that means it is having some light, and we want some parameters for that specular. So those parameters are these. These are the 4 parameters for the specular. And for the, again, with this material, we are also telling that with respect to the shininess, the value is 50, and we are also specifying matte shininess with these values also, the shininess values. Okay. And apart from that, we also have a light V, where the first parameter speaks about the light, but what sort of a light we have. So we have the position of the light source, and for this light position we have given XYZ axis. Okay, so these are the XYZ axis. So what I'll do is I'll show you an example where XYZ both are 1. That means it is on the if we consider this as Z, I mean the near as positive Z. Okay, so my port source is somewhere over here. Okay, what I'll do is I'll just negate the value of x. So negate the value of x means it should be a mirror of light. Okay, so here I'll make it as a negative. So compile and run. So can you see the light source? The light has been shifted towards the other side, which was there in the previous. Can you see that, guys? Anybody, please let me know. All right, then we'll stop at this point.